Good morning, guys. If you can give me some green check marks, please. We'll get going here in a second. Thank you, thank you. The other thing we need to do is wrap up section 9.1. I kind of left you guys at the end of class last day with a bunch of questions. I said, just give them a shot. Some of the acceleration due to gravity stuff, objects in free fall is a little bit tricky. So I wanted you just have a look at it. We kind of ran out of time. So spend a bit of time talking about that, and then we'll finish up unit 9.2 today, which is graphing accelerated motion, and then that's it. Next day we'll have some review on Thursday, and then we'll see what we think for the following week if you guys want some more review. Monday, Tuesday we don't have anything scheduled other than just review, so we'll see what that looks like. I had a look at what I want to call the draft version of the final, or midterm number 2, if you will. And I have it written down here. I counted out 24 multiple choice questions on the chemistry unit. Then there was chemistry, of course, was units 4, 5, and 6. So those 3 units together had 24 questions. 5 questions on unit 7, which was the radiation, half-life, isotopes, that sort of stuff. And then 16 questions on the physics unit, which would be 8 and 9, which obviously we're just kind of finishing off today. If you're counting along at home, that would total about 45 multiple choice questions. And then we'll probably do 5 or so written questions. And think about 1 from each unit written sort of thing. And that'll be the test. It'll be probably between 50 and 60 marks. And we'll expect it to take about an hour and a half to complete. So does anybody have any questions on that? Of course, the date for that next Wednesday. No questions? All right. Did anyone have any specific questions out of the learning guide from last day? Anything specific they wanted to see? I can go through those. Sorry, I'm in the wrong tab here. Yeah, we can definitely do that. Kyla, anything else? Page 3, number 15. Yeah, I got that much. Looks like somebody last year had the same question. All right, number 15 here says a car is going 100 kilometers per hour, passes a bystander, then passes another bystander 20 seconds later when it's going 120. What's the car's average acceleration? All right, so we want to figure out the acceleration, and we know from the formula sheet that, jump over to the data book, all the acceleration formulas are in this second and third set. So you have accelerations, change of velocity over time, change of velocity is acceleration times change in time, and change of time is velocity over acceleration. And then you have your 3 change of velocity formulas. Delta V is VF minus VI, and then just rearranged. So again, essentially these formulas, there's only 3 formulas. This guy, and this guy. And then the table shows the permutations of the formula. So if you wanted to solve for VF, you look at this one here. If you wanted to solve for change in velocity, you can look at this one. If you wanted to solve for time, you can look at this one. So 3 formulas, you don't have to memorize them, you get your data book. But they show you all the different permutations of those formulas. So we're asked to find the acceleration, the average acceleration. So we're going to need acceleration's change in velocity over a change in time. So I'm going to start by writing down my formula. Acceleration is a change in velocity divided by a change in time. Now, I guess the reason this question is kind of tricky, and this is probably why you brought it up, Kyla, is that we have units here. So we have an initial velocity, we'll call it VI, and then we have another velocity here, we'll call this VF. And then we have a time, which is over here, 20 seconds. It's going to be our time. And we're trying to find the acceleration. It says, what is the car's average acceleration? So that's what we're trying to solve for, which wouldn't be terribly difficult, but if we look really carefully at the units in the problem, we have two velocities in kilometers per hour, 100 and 120, and then we have a time in seconds. And the time in seconds is the tricky bit because our units have to match up. So we can do two things. We could either convert our velocity into meters per second, or we could convert our time into hours. Doesn't matter which one or which way you'd like to do it. Kyla, do you have any preference? I would probably, you don't have a preference? I would probably convert the time into hours, because if we convert the velocity into meters per second, we have to do it twice. But converting the time into hours, we only have to do one calculation. So maybe we'll start with that. I have 20 seconds, and I know that 1 minute, I guess we know the conversion here. Let's just kind of skip right to the chase here. 1 hour is 3,600 seconds. So why did I put seconds on the bottom? Well, if I have seconds on the top and the bottom, it cancels, and I'm left with units of hours. And we've done some of these calculations before, where we converted meters per second, kilometers per hour, and vice versa. So we're going to go 20. We're going to get a really small number because 20 seconds isn't very long in terms of an hour. So I'm going to go 20 divided by 3,600. And I'm going to get 5.5555 times 10 to the negative 3, or 0.005, we'll call it 6. Hours. Okay, so that's kind of one step along the way, converting our time into hours. The other thing we need to do is we need to figure out our change in velocity. Now, just looking at the question, we can see that we have 120 and 100, so our change is 20, but we should be able to kind of quantify that. So I could do it in one step and just do it all in the equation here, or I can do it in 2 steps, because I need to figure out what the change in velocity is. So delta V is V final minus V initial. Change in velocity is going to be 120 minus 100. It's going to be 20 kilometers per hour. So that's going to be in there. I've got my time in hours now to go on the bottom, and I'll just solve. So I have 20 kilometers per hour divided by 0.0056 seconds. Now, this number is going to be a little bit strange because the units don't really make sense, but 20 divided by 0.0056 is 3,571. Sorry, should be hours. Kilometers per hour squared, which isn't a typical unit. I have a feeling the answer is probably in meters per second squared, but that's just as valid of an answer. Kyla, does that make sense? Confuse you more? Kind of get where we're coming from there? a little sense. It's all we can hope for, is a little sense in the world. All right. Does anybody have any additional questions from that section? 9.1? Anything else? Maybe I'll just pick a couple of the objects in free fall, and I'll go through those, and then we'll look at the next section. Is there no objects in free fall? Let's do number 12. Kind of like number 12. A ball is thrown straight up into the air at 14 meters per second. How long does it take for the ball to slow down to an upward velocity of 6? So I always like drawing pictures. We have an object, we throw it up. It's initially leaving our hands at 14, and then it's going to travel up in the air. When it gets to the top, the velocity is going to be 0, and then it's going to just come back down. So we want to know how long does it take. So we're trying to find a time for our ball to reach a velocity of 6 meters per second. So if we have another look at the question, we can start identifying the variables and things we have in here. So we have this 14 meters per second is how fast it leaves our hands. So that's going to be your initial velocity. The question's asking how long does it take. So we're trying to find time. And then we have another velocity here, a final velocity of 6 meters per second. So because we're trying to find time, we should pick the equation that has time isolated already. And that is down here. So time is our change in velocity divided by our acceleration. Looking at this guy down here. I don't want to close it. Please don't make me close it. Please. All right, we'll just let it close, and we'll reboot it. Yeah, I know that something has caused it to stop working. Let's see if we can't just sort this out. Okay, go away. Thank you. Let's launch it again. There we go. So change in time is, what did we say? Acceleration, velocity over acceleration. All right, now anytime we have an object in the air, falling, thrown, things like that, we know the acceleration. And the acceleration is always going to be negative 9.8 meters per second squared. That is the acceleration due to gravity for any object in free fall. We also have a change in velocity. So our change in velocity is going to be our final velocity minus our initial velocity. And we've identified these in the problem already. So we said the final is going to be 6. And the initial is going to be 14. So 6 minus 14 is going to give us, what's that? Negative 8 meters per second. So we can plug these numbers into our equation now. I'll just keep going over this way. So our change of velocity is negative 8 meters per second. Our acceleration is negative 9.8 meters per second squared. 8 divided by 9.8, 0.81 seconds. And we don't need to include a direction with that because it's time. And time doesn't have a direction associated with it. And notice that if you hadn't kept your negative signs there, you would have had a negative time, which would have been a problem. It's a little tricky to go back into time. We can, maybe. Maybe you guys will figure out time travel, hopefully. Save the world. All right, does anybody have any additional questions out of this section now that you've seen a couple more, had some time to think about it? Negative, negative, negative. All right, I just wanted to show you guys one little thing, like a little demonstration that I think does a really good job of talking about objects in free fall and talking about air resistance. So last day we kind of finished off with a video of objects on the moon, where, I forget the guy's name, but he dropped a hammer and a feather and they fell towards the ground. And they hit the ground at the same time. You couldn't really see it well. The frame rate's kind of slow. But what I have here today is, just move this out of the way. I have a trusty science textbook, Science Probe 10, which isn't really good for anything but dropping because it's an old book. And I have a piece of paper, or several pieces of paper here. All right, so if I drop the textbook and the paper, which one's going to hit the ground first? What do you think? The book. So we've got a couple of votes for the book. Why do we think the book's going to hit the ground first? So we got it's heavier. Okay. So this gets back to the idea of objects in free fall. Does the mass really matter? So let's do it. We'll try it and see if you guys are right. So I drop them. It's going to be loud. All right. So obviously the book hit the ground first because it was heavier. All right. All right. I'll give you that. What if I grabbed a pencil and a book? And I drop these two things at the same time. Which one's going to hit the ground first? The book. We got a couple votes for book again. All right, let's try it. I'm going to do my best. It's kind of tricky to drop two things at the same time, but get an idea. I drop them. Which one hit the ground first there? We can do it again. It'd be really great if we had like a super slow-mo replay where we could kind of watch it back. All right, what do we think? You guys with a keen eye at home, which one hit the ground first, the book or the pencil? Book, pencil, book, pencil. So it looked kind of equal. They hit at the same time. Jesse thinks, yeah, in reality, if we were in a perfect situation here and I had some sort of apparatus that would drop these at the same time, then they would, hit the ground at the same time. So let's go back to this paper for a second. You guys said, okay, the book and the paper, if I drop them, the book hits first because it was heavier. But then when I drop the pencil, which was obviously much lighter than the book, take my word for it, it's not a very heavy pencil, they hit at the same time. So does the book hit the ground first because it's heavier? All right, Josh, we're getting there. Let's answer my questions. I'm going to kind of string you along here today. So does the book hit the ground before the pencil because it's heavier? Or does the book hit the ground before the paper because it's heavier? So Josh is on this idea of air resistance. What does that have to do with anything? When I drop the pencil hit the ground at the same time as the book. So was air resistance a factor with the pencil? Maybe, maybe not. What do we think? It's more aerodynamic. The book is more aerodynamic than the paper. I'm going to give you this little visual here. If I put the book and the paper together, they have the exact same surface area. So think about that for a second. They have the same surface area. So they would have the same air resistance, would they not? Have you scratching your heads now? The pencil, you would think, would probably be more aerodynamic than a book. I would agree with that. I mean, there's less stuff there. How about this? If I took the paper and I crumpled it up, All right, the paper is still the same piece of paper, but now obviously I've changed the surface area of it. I haven't changed the mass though. The mass is still identical. If I drop these two things now, which one's going to hit the ground first? More weight, more air displacement. I like it. Paper still weighs the same. Surface area has changed a little bit. So book and paper, I wish I could drop this book a little bit better, but all right, what did we think? We can do it one more time. What's going on? Same piece of paper, I didn't change it, still weighs the same. If I drop these two things, I can do my best to estimate that they both hit at the exact same time. So when we have objects that are falling, it's really important to remember that any object in free fall, when we are dealing with it in our perfect world, the mass doesn't matter. It doesn't matter if it weighs as much as a piece of paper, really light, or it weighs as much as a textbook. If I drop these things, they're going to fall at the same rate. So we can ignore air resistance. And one really interesting thing to show here is that if I take another piece of paper, again, if I drop these, the book would fall faster because this has air resistance. But it does have a little bit to do with shape, yeah. What if I did this? So I've taken the piece of paper, and I'm just going to put it right on top of the book. And what if I drop this now? What do you think is going to happen in this situation? Is the paper going to stay here and fall kind of slowly down like it did before and the book drop? Or are they going to stay together? What's going to happen? Try this. Ready? 1, 2, 3. What happened to the paper there? What do we think about that paper? Again, if I drop them side by side, obviously the book hits. The paper still weighs the exact same amount. I haven't changed the paper. It's still the same piece of paper. If I now hold it up, the book and the paper fall at the exact same rate. So if I eliminate the air that's pushing up the paper, the air that's kind of the paper's trying to fight through, if I put it on top of the book, they fall at the exact same speed because I don't have to worry about the air resistance of the paper anymore. So just something to think about, kind of scratch your head about when you're dealing with objects in free fall. You definitely don't have to worry about air resistance. And when you kind of remove air resistance from the equation, everything will fall at the exact same rate. Whether it's a piece of paper, or it's a book, or it's a pencil, they're all going to fall at the same speed. And when you are in a perfect environment, that's what's going to happen. So I had that video from last day. We never actually got a chance to watch it, but it's really cool. Maybe I'll just grab the last little bit of it. So I mentioned it briefly. NASA has a big vacuum chamber where they test things like Mars rovers and lunar landers and things like that, where we are sending these objects to places with little to no atmosphere, putting things in space. And basically it's this huge chamber. I'll give you guys the link to the video, but we'll just watch a couple seconds of it. Kill my sound here. I'll just throw it in chat. You guys can maybe just watch it after class or later or whatever. And we'll just watch kind of the good bits here, kind of in the sake of saving some time. So Brian Cox visits the world's largest vacuum chamber and basically repeat the experiment that they did on the moon with this one has a bowling ball and a feather. So they crank it up into the air and then let it go. And as you would expect, the bowling ball drops really quickly and the feathers take a long time to hit. Kind of gives you a really bad frame rate of what's going on. So what if they close the door? That's what's going on here. This is how big this building is. It's absolutely massive. So they're going to close the door, and they're going to take a big vacuum, that's what it's called, and pump all the air out of it. And so there'll be zero air resistance now. I'll just play this through. The frame rate again is going to be really bad, but it's in super slow-mo, so you get a bit of an idea. So there's no air in this room now, and you can see the bowling ball and the feather are falling at the exact same rate, which is just amazing. Notice the feathers don't move at all. They just keep falling. They don't change their shape. You would expect them to kind of catch some air and do some crazy stuff. But I'll see if I can grab the exact frame just for the sake of speeding things up. All right, so you can see right there, the feathers haven't changed their shape at all because there's no air in this room, and the bowling ball is, falling at the same speed as the feathers, and this kind of proves that in the absence of air, resistance, so in space or in sort of a situation like this vacuum, you're going to have an object, regardless of mass, regardless of shape, they're all going to fall at the same rate, which is pretty cool. So if you guys want to watch that full video later, you can. It's a good one. I'd recommend it. We got some stuff to get through. So there you go. This is the last section of the year, and it is just kind of more of the same. So graphing, accelerated motion. So we did in Unit 8.1, we talked about velocity and displacement, distance, and the difference between these words, and then we looked at graphing it. Now in 9.1, we talked about acceleration, change in velocity. Now we're going to graph it. That's kind of how this goes. So the challenge for you guys as students is when you see a graph on a test, when you see a graph on a final exam, you need to be able to identify what type of graph you're looking at. Because if you're looking at a velocity time graph, it's going to have different meaning than a position time graph or an acceleration time graph, which aren't quite as common. So we know this already. The acceleration of an object depends on the change in velocity and the time required. And when stopping a moving object, the relationship between time and acceleration is increasing the stopping time decreases the acceleration, and decreasing the stopping time increases the acceleration. This is how airbags work. If you imagine your face hitting your steering wheel, your face stops extremely quickly when you hit a steering wheel with it, which is generally a bad thing. But an airbag inflates, and once your face hits the airbag, it takes the amount of time your face would take to stop, and it kind of extends it a little bit. Even fractions of a second lessens the acceleration impact quite substantially. So that's how airbags work. If you watch any people like stuntmen jumping out of a building or something, they have those big air cushions. So it takes, when you land on the top of the cushion, you kind of slows down, or it increases the amount of time it takes to go from going really fast to a complete stop, lessening the acceleration and lessening the impact and damage. So we need to talk about lines of best fit. It is in the course, and it's a pretty important concept, especially for science people who will continue on. So a line of best fit is a line that represents the data. So if I had a bunch of data points, let's say I have a distance time graph. I have a point here, a point here, a point here, a point here, and a point there. And I wanted to connect these points with a line to represent the velocity. Slope of a distance time graph is going to be velocity. So pull out my trusty ruler, in this case, edge of my calculator, and I draw a line. Now, I want to hit as many of these points as I can, but sometimes I'm not going to go through all of them. And that's okay. And basically what's happening here is that in the real world, if I was collecting data, I said, okay, stop my watch now, how far did it go? A little bit further, how far did it go? And I actually plotted what that looks like. Sometimes you end up with a point like this that isn't on your line, and that's okay. Maybe you made a mistake in calculating it. Maybe something like happened, it hit a bump, your object, a little toy car or whatever. It doesn't match the other data points, and that's fine. There's nothing wrong with that. So that's what a line of best fit looks like. It's also important to note that a line of best fit doesn't necessarily need to go through the origin. Your line does not have to go through the point 0, 0 here. If your data points look like that, and you want to draw your line, up through there, that's fine. This point is no more important than any other point. So if you're drawing a graph, don't think that you must go through that point. You don't have to. It's not special. It just happens to be where time and position are both 0, but you don't necessarily have to go through it. Another thing is this: when you start plotting data from real-world examples, you could end up with some data that kind of looks like all over the place. And if you draw a line of best fit through these data points, there's nothing that says you have to hit any of your points. Sounds kind of weird, but you want your line to be representative of all your points. So in this case, I have 3 points above my line, 2 points below my line. My line's a little bit closer to these guys up here on the top just because it's kind of an average, but it doesn't go through any of my points, which is fine as well. But that line represents that data set as best as you can. So this is how a line of best fit works. It's a line that represents all of the things that you are graphing. It doesn't necessarily have to go through any of them. It might miss one of them. It doesn't have to go through the origin. So you'll probably see a question on line of best fit. It's an important idea, but just do what you can to figure out what a line of best fit is. So again, it's just a line that kind of represents the data as best as possible. All right, so how can you easily tell if there's acceleration on a distance versus time graph? So acceleration means an object's speeding up or slowing down. It's not traveling at a constant or uniform rate. So is there anything that kind of you would think, maybe even looking at example number 3 below, what's a little bit special about example 3 or this line here compared to most of the lines that we've seen up until this point? What makes this line look different than the other lines we've been drawing on our graphs? It's blue. We haven't seen any blue lines yet. So every single graph we've drawn up to this point has had a completely straight line. And this line is curved. So what does that mean? So if I go back to our, let's plot a distance versus time graph, and we'll start off like really slow, and then we'll do something like that. Let's talk about what this means, what's going on here. So we know the slope, hopefully, of a distance versus time graph is equal to the velocity. So if I were to take the slope of the line at this very beginning portion down here, just kind of approximate it, would you say that slope was steep or not steep? Would it be really fast velocity or really close to zero velocity? What would you say that red line, this guy here, is kind of representing? Fast motion, slow motion? If you had to guess. That'd be definitely slow motion. The slope isn't very steep, it's almost zero, so it's going, yeah, you're good, you're good. So it's going really slow. What if I took the slope right here? Compared to the first slope, would that second line be representing faster motion or slower motion than the first line down here. And then what if I did another slope up here because I wanted to figure out what was going on at that third section. What's happening to the slope? Is it the slope increasing or decreasing? Is this object going faster or slower? What do we think? It's going faster. So initially it's starting out really slowly, and then kind of in the middle of the line number 2 there, got a bit of a steeper slope, so it's speeding up a bit. And then line number 3, we have a really, really steep slope, so it's going even faster. So up until this point, all of the lines we had drawn on these graphs would have been completely straight lines. But now we have accelerated motion, non-uniform motion, and our object's going to start speeding up. So when we talk about distance versus time graphs, how can you tell if there's acceleration on a distance versus time graph? And it's really important that we are just talking about distance versus time graphs. We have a curved line. So if the line has a curve to it, that means you are dealing with accelerated motion. And looking at example 3 here, we have a distance versus time graph. The question asks, is the velocity getting bigger or smaller? So if I took the slope here, called that 1, took the slope here, called that 2, and took the slope here, called that 3, what's going on? Is the object speeding up or is the object slowing down? Consider the slope. We have a slope like this to begin with. It's like this, sorry. And then it goes to here, and then it's completely horizontal. So what's happening there? It's definitely slowing down. If we took that third portion of the graph, it's completely horizontal, so it's stopped moving. The position staying the same. Time ticks on. The position isn't changing. So you have a steep slope. Steep slope is going fast, slowing down a little bit more, and then coming to a complete stop. So the velocity is getting smaller. And at the end of the trip, it stops. All right. Let's look at a couple more examples here. Consider the distance versus time graph. So we've identified these both as being distance time graphs. The first one, example 4, is the velocity getting bigger or smaller? What's the velocity at the start of the trip? The graph doesn't go through the origin. What does this tell you? All right, so trying to understand what's going on here. We have a curved line, so we know our object's either speeding up or slowing down. Example number 4, is it getting bigger or smaller? Is the object speeding up or slowing down? Let's just take a couple of slopes here. I got a slope there and then a slope there. So comparing slope 1 to slope 2, what's going on there? Yeah, it's definitely speeding up. That slope is increasing. So the velocity is increasing. What was the velocity at the start of the trip? So right at the beginning, what was the velocity here? What does it look like? Right there. A little bit hard to see maybe. We were to take a guess at that. 0-ish. I'd go with that. And then, this is a super important point. The graph doesn't go through the origin, meaning that it doesn't start down here. So what does that tell you about the car? You might have to think really hard about what this means in terms of distance versus time. So we don't go through the origin. We don't start our line here and kind of follow that same curve up. So what does that mean? What does it mean when we start right there? What's the significance of that? Started measuring late. So that kind of almost implies time, Eric. And that's not necessarily what we're dealing with here. I have a little picture here of a beautiful tree and a car. maybe a bit of a hint as to what I'm trying to get at. All right, so here's my car. Let's say I'm 2 meters away from the tree. What would that look like on a graph? Yeah, Eric, you got it. So if I look at the graph again, let's pretend like there's no numbers on this graph, but I can just put in numbers as long as they're kind of relative to one another. That's fine. If this is 0 here and I make this 2 up here, it just means that my object is a certain distance away from something. It's starting 2 meters to the right of some object. So when I have a line that doesn't go through the origin, it just means that I'm starting at some position relative to something. So my object, my car, whatever we want to call it, spell right, starts. We'll go some distance in front of something. So makes it a bit tricky here because we don't have numbers to deal with. We don't know what the object is. We just have a little graph to kind of interpret everything from. But we can just do our best. I like making up stories. It seems to work pretty good. So all of the ones we've looked at so far have had these graphs kind of like, increasing this way, going up. But now this next one, example number 5, we have a graph that's dropping down. So what's going on here? Consider the distance time graph. Is the velocity getting bigger or smaller? What's the velocity at the start of the trip? And the distance is getting more negative with time. What does this tell you? So let's look at the slope here and then look at the slope here. So we have first slope and our second slope. If we want to compare those, what would we say is going on with the object here? Is our slope increasing or decreasing? Decreasing, question mark. I'm with you on that. What is it doing? It is kind of decreasing because it's going below the axis. What does that really mean though? Increasing? It kind of is increasing, but it's decreasing at the same time. We just need to kind of get what it means to be down in this world, under the x-axis. Rainbows and butterflies down there. You betcha, Kyla. The slope's increasing, for sure. The slope is increasing. But it's increasing in a negative way. So does it make sense to say decreasing or increasing? It's confusing. So we have a negative slope. And a negative slope means negative velocity. So all that's going on here is that we're starting off going backwards really slowly, and then we're speeding up going backwards. So when Kyla said decreasing at the beginning, I was like, well, that kind of makes sense. And then Eric's like, oh, increasing. Well, that kind of makes sense too. So what's going on? We have a negative velocity. We're increasing our negative velocity. So we can kind of think about it as decreasing, I guess. Guess I could write it down. Increasing our negative velocity. All right. The distance is getting more negative with time. It's kind of this last sentence we still need to dissect. What does this tell you? What does it mean when our distance gets more negative with time? Is there anything significant about that? If we'd kind of had the mirror of this graphic, if our slope had gone up, what would that have meant our object was doing? The slope's just kind of mirrored, it's flipped. It's going kind of down in a rainbow. What does that mean? What if we didn't have slopes changing here? What if we just had a nice straight line here and a nice straight line here? What would that have meant? Let's just talk about the positive situation for now. If I have if I had just that positive line increasing, going up, that just means it's moving away from something in a positive direction. Eric, you're on the money here. If if I have this curvy line going down, the rainbow, it's just moving away from something in the negative direction. So if I had, you know, a tree, and then my car would just be on this side of the tree, moving that way. It's a great looking car. So it just means it's moving in a negative direction. So increasing its negative velocity, and we could write moving in a negative direction. Yeah, that's it. We got it. All right, so those are distance time graphs. Curvy lines just mean it's accelerating. It's getting faster. Now we're looking at velocity time graphs. So this is where it's really, really important. When you see a graph, you don't just assume it's a distance time graph. You need to look, is it a velocity time graph? Is it a distance time graph? Is it an acceleration time graph? Because we're going to have all different scenarios now, these 3 different types of graphs. So the velocity of a uniform motion can be represented by a position time graph. The velocity changes, we can write it on a velocity time graph. So an increasing slope, if we think about what's going on here, if we look at 1 second, we're going 10. At 2 seconds, we're going 25. At 3 seconds, we're going 35. At 4 seconds, we're going, I guess that's not 10 down there, but close enough. At 4 seconds, we're going 50. So as time goes on, our velocity is increasing. So that's what an increasing slope looks like, or a positive slope. And that means it's accelerating. So we're going slowly, getting faster, faster, faster. It's accelerating. It's increasing its speed. So on a distance time graph, if we had a distance time graph of the exact same object, we could do a distance time graph. It would look like this. Our velocity is increasing, our slope is increasing if this were a distance time graph. So these 2 graphs would represent the exact same object, but they look very different. One's a velocity and one's a distance. So it's important to kind of figure out what you got. The slope of a velocity time graph, try to speak clearly. This is super important. The slope of a velocity time graph is going to give you your acceleration. So if you ever want to find the acceleration, you can find the slope of your velocity time graph, and that'll give you the acceleration. Just like we took a slope of a distance time graph to find velocity. Same thing here. All right, again, super important we identify what type of graph we're dealing with. So we have a velocity time graph. No numbers, but it's okay. We can kind of figure out what's going on relatively speaking. Positive slope, positive acceleration. Negative slope, negative acceleration. Zero slope, uniform motion, traveling at a constant speed. As time ticks on, you're still going the same speed. All right, so state which time interval the acceleration was 0. So we have these times, time 1, time 2, time 3. In which time interval, after what time or time interval, is our acceleration 0? In what one are we not speeding up or slowing down? Remember, slowing down is just negative acceleration. What do we think? T1 to T2, Eric says. So from here to here, we'll call that A. You know, the object's traveling at a constant velocity. We don't have a number. I could give it a number. Let's make this number 20 up here if you want. 20 meters per second. As time ticks on, I'm still going 20, 20, 20. So I'm not speeding up, slowing down. Letter B asks for the acceleration being negative. So in what time interval did we have negative acceleration? We're looking for a negative slope. That's happening between 2 and 3. Positive slope is letter C. That's happening between 0 and 1. And then object increasing its velocity north. Increasing its velocity north. So if I look, I can see that the velocity is north, being measured north. I probably have a 0 velocity down here. I said this is 20, could be anything. So it's increasing its velocity going north over here, and decreasing its velocity north, that would be over here with our negative slope. And then constant velocity north is a horizontal line, or up at the top. So those are kind of the scenarios you'll encounter. In terms of velocity time graphs. Are we all right there? Does anybody have any questions? Confused about something? Don't get it? Need help? All right, let's look at a couple examples, and then we'll look at the learning guide, and then we'll maybe call it quits. Sketch a velocity time graph for an accelerating car. Appear if it accelerates constantly from rest to a velocity of 25 in 10 seconds on the graph. Show its slope, question mark, what does the slope? It's just very poorly worded. That's okay. All right, so we have a graph. We're just sketching it. Doesn't have to be beautiful. We have a velocity time graph. All right, so we want to sketch a velocity time graph for a car. It's accelerating from rest to a velocity of 25. So let's put a 25 up here. It's going from rest to 25. So what is a velocity of rest going to look like? That means it's not moving. And if this is a velocity time graph, rest is going to be down here, indicating zero velocity. It's going from 0 to 25 in 10 seconds. So I'm going to put another point out here. This is 25, and this corresponds to 10 seconds. So drawing my line with a ruler. There we go. So I'm going from 0 to 25, and that's taking 10 seconds. The slope, which it's also asking me to find, is rise over run. And in this case, the rise is 25, and the run is 10. So I can draw in a little triangle here. Rise this goes from 0 to 25, and the run is 10. This is 10 down here. This is 25 here. 25 divided by 10. It's going to give me 2.5. Pardon me. 2.5 meters per second, or meters per second squared. What does that slope represent? Meters per second squared should jump out at you as being the acceleration. So that is the acceleration of that object from 0 to 25. All right, example number 2. Consider this velocity time graph. Is the velocity getting bigger or smaller? The graph doesn't go through the origin. What does that tell you? All right, what do we think? Is the velocity increasing or decreasing here? Again, there's no numbers. We can put numbers on here. I'm going to put some just imaginary numbers. That's 0, make that 10. This will be, I don't know, what's that looking like, 3? Definitely increasing. And the second part of the question is it doesn't go through the origin. It doesn't go through this point down here. So what does that mean? What can we learn from that? Or what can we get? What's the significance of starting here and not down there? At time equals 0, so this is 0 seconds here. We can put 10 seconds out here maybe. At time equals 0, how fast is the object going in our imaginary world, where I put in numbers that weren't necessarily the right numbers but didn't really make things any different? at 0 seconds, it's going already 3 imaginary units. So when time starts, the object's moving. So before we even start our stopwatch, this car or ball or whatever, it's already rolling. It's already moving. The car is moving somewhere. Time equals 0. It's already going. It didn't start from rest. If it had gone through the origin, if we had another graph and we had the same line going from here, and this is a velocity time graph, that would mean we're starting at rest. But that isn't the case here. We have this increased velocity to start. All right, let's look at the last one here. Consider the velocity versus time graph, the acceleration positive or negative, and what's the velocity at the end of the trip. So example number 3, our line is going down to the right, so we know that's a negative slope. And the slope of a velocity time graph is the acceleration. So negative slope is negative acceleration. And the velocity at the end of the trip. So we go to the last point here. What's our velocity there? What do we think that velocity is? What is this significance of this horizontal line? What is the velocity here? Let's make this 20. Let's make down here, and we can make that negative 20. What's the velocity right in the middle? The velocity at that point is going to be 0. Anything on the line is going to have a 0 velocity. Consider this one. So we have a velocity time graph where we start out really fast and then it goes to 0. And then again, we can put in imaginary numbers. We'll make that 20, we can make that 0, we can make that negative 20. So what's going on? What happens here at this point where this line crosses the axis? What's significant about that? We can see that it's starting at 20, starting up here. What happens when it crosses the x-axis there? What's its velocity at this point? It's the exact same as the previous question. We said when we cross that x-axis, our velocity is, we're going negative. When we get down here, for sure, we're at negative 20. So here the velocity is 20 forward. Here the velocity is negative 20 or 20 backwards. But what happens right in the middle? This point. What is our velocity there? It is indeed 0. So we're going forward 20, then we stop, and now we're going backwards. So what does that kind of look like in terms of motion? Means that as soon as you start recording or start timing, you're slowing down. You're going 20, 18, 17, 16, 15, 14, 13, 12, 10, 0. Now you're going negative 1, negative 2, negative 3, negative 4, negative 5, all the way to negative 20. So as time goes on, you're going slowing down, starting going backwards, slowing down, forwards. Now you're going 20, 19, 18, slowly, slowly. You stop, and then you're going negative 1, negative 2, negative 3. So it would be like stopping and then moving backwards. That's kind of the motion being described there. All right, let's look at the learning guide. Section 9.2, graphing with acceleration. A tangent line we didn't talk about specifically, explicitly, but enough of OneNote for today. All of those little red lines I was drawing up at the top, which now I won't be able to look at, those little red lines are tangent lines. So if I have a curve, and I just have a kind of a straight line that touches the curve, that's called a tangent line. So when I was drawing those little red lines, putting 1s and 2s next to them, I was saying, okay, what does this mean? What's the slope here? And then the slope increases, and then the slope increases even more. Those red lines were tangent lines. So when you have a curve, you can't take the slope of a curve, but if you draw a line that just touches the curve at one point, it's called a tangent line. There's some other questions, and I really wanted to look at the last question because I think it's a really good question. Let's see if I can restart OneNote. All right, so you have some velocity time graphs, finding the area under the graph. Never talked about that, we should. All right, let's have this is obviously a velocity time graph. Use both area and the equation to determine the velocity and the displacement. So we have a velocity time graph. We've identified what type of graph we have. If I want to find the displacement from this graph, just looking at it kind of doesn't make sense because I don't have a distance time graph. It's a velocity time graph. But let's just think about this for a second. If I had the area of a rectangle, that's going to be length times width. So let's call from here to here length, and from here to here width. So my length in this case is going to be in seconds, and my width, just bear with me here, my width is in meters per second. If I multiplied seconds and meters per second together, what happens? Well, the seconds cancel on the top and bottom, and I'm left with units of just meters. So that means that if I take the area under the graph, I'm going to get displacement. So in this particular example, the area is going to be the length of 5 times the width of 10. So this is 5 by 10 equals 50 meters. So I can find out how far an object went by taking the area under a graph. It doesn't come up very often, but it is in the learning guide. The second question, number 10, is the same thing except you have a triangle, so it's base times height divided by 2 to find the area of that. And number 11, these questions are really really good. So what I'd like you guys to do is, it's 10:30. I want you to take 10 minutes and try question number 11 just to figure out what's going on. Identify if you're talking about a velocity time graph, a distance time graph, or an acceleration time graph, and attempt to describe the motion. I'll show you maybe one or two and then give you guys some time. So let's get rid of this stuff. Chemistry on there as well. Let's look at the first two here. So if I have a horizontal line on a distance time graph, it means as time is going on, I don't have distance changing. So it really just means object's not moving. So that's all I would write in. Object's not moving to the left of another object, or just object's not moving. The second graph here, I have a velocity time graph, and I have a positive slope, so it means my velocity is increasing. I could just put in numbers, but I don't have to. And it just means it's accelerating. I have positive slope, means the object's accelerating. So go through the rest of these and see if you can describe the motion. Just describe it going, velocity is increasing, decreasing, constant motion, uniform motion. Use words like that. Try to describe what's going on. You know, slope is steep, so it's going fast, and then it goes to 0. Or the slope is a curved line, so it's accelerating. And just do your best to describe that. So I'm going to put up 10 minutes, and I'll see you guys back in 10, and we'll take up some of these questions. Thanks. All right, guys, welcome back. If you can give me a green check mark so I know you're alive. Maybe? Some of you? Excellent. All right, let's just do a couple more of these, and then I'll leave some for you guys to sort out when you submit the learning guide. The important thing here is we can identify what type of graph we're dealing with, and then try to think about what that actually means. So, see let's do this one here. Velocity time graph, it's a horizontal line. So up at the top, we had a distance time graph that was a horizontal line. We said the object's not moving, it's just stationary. So what about a velocity time graph with a horizontal line? What does that mean is happening down here? So if you're ever confused, you see one of these graphs and things don't really make sense, just put in numbers. So I'm going to put 0, maybe this is like -5. I'll put +5 up here, and then we can have like 2 seconds, 4 seconds, 6 seconds, 8 seconds. Something like that. So the object is traveling at -5 seconds, or -5, and then it's traveling at -5, and then it's traveling at -5, and then it's traveling at -5. So if we were to describe this motion, how do we describe it? What would we say is going on here? It's constant motion or uniform motion for sure. So just a constant velocity. And notice what we said up above. When we had this object, it was a distance time graph, and it was this horizontal line. The object wasn't moving, but now we've got a velocity time graph and a horizontal line, and the object's traveling at a constant velocity. So it is moving. So this is why it's so important to establish whether you have a velocity time graph or an acceleration time graph. Let's look at a curved line, try to describe what that is. A couple here to choose from. Let's look at this one down here at the bottom. So we have a distance time graph, and if we were to draw a tangent line, we would try to identify what the slope is here. So I have a really steep slope, and then a slope that's not as steep, and then 0 slope. And we have a velocity being measured here because this is the distance time graph, and the slope is velocity. So we have this really steep slope to start with, then not so steep slope, and then a 0 slope. So what's going on with our object? It's accelerating, it's changing its velocity. Would we say it's speeding up, slowing down? It looks like it's really steep to begin with, so it's going fast, and then slow, and then stop. Definitely slowing. Just because it's below the x-axis only means that it's in a negative direction, so it's just moving away from something. So it's slowing down, and because it's below the x-axis, or the slopes are all negative, in negative direction. Maybe we'll look at one more here. Something like this. We have a distance time graph. We've identified it as d and t. You have this really steep slope, and then you have kind of a horizontal slope. Sort of two parts to it. So if we look at the first part, talking about this, what's going on here? And then what's going on here, these two sections? The first part and the second part. It's moving then stopping. That's brilliant. So we have a slope here, and the slope is positive, so it's moving forward. And then we have 0 slope, so it's stopped. So I think moving then stopping is a concise way of describing this. I would go moving forward, then stopping. And that works for me. So have a look at the rest of those, see what you can do. Did anybody have any questions before we log off for the day? Essentially, next day I will answer any questions you have on Unit 9. Some of you guys have submitted Unit 9 already. You just kind of were like, I'm done, ready to move on. Get on with the final exam and studying and things like that. So next day we'll start with any questions you guys have from this. We'll maybe talk a little bit about review, and I can go through a couple of the provincial exam questions, stuff to look at. And then we'll see what you guys kind of feel at the end of next day as to whether we want to do class or not next week on Monday and Tuesday. It's kind of up to you. Mr. Ross, did you plan anything for Thursday this week coming up? No, I think I mentioned to you that we wouldn't be in here, but maybe we will, if that's all right with you. Yeah, so next class we'll meet in Blackboard again, go over any questions you guys had on the Unit 9, and we'll just plan on spending the majority of next day's class just kind of reviewing stuff. So obviously if you want to submit the Unit 9 learning guide, I'd be happy to mark it and get the password out to you. But we'll spend time finishing it up next day. If you have some questions, if you don't have questions, it should be in at the end of this week. And then we'll just look at some review. And again, the test will be probably about 45 questions multiple choice and about 5 written. That'll be next Wednesday. So if nobody has any questions, we'll say see you later. If anybody has anything pressing. All right, well that's kind of it for the course material. You guys survived it, and everything kind of now is up to you guys. Finishing the work, reviewing, studying for the final or second midterm, I guess, not really a final exam, is up to you. So you're going to get out of it what you put into it. If you sit there, twiddle your thumbs, that's fine, I guess. But if you spend some time going through the material you don't understand and trying to relearn things and going back and reviewing, you should do well on the last little test here. So thanks very much, guys. I hope you have a great weekend. Not weekend, it's Tuesday. Hope you have a great couple days, and we'll see you on Thursday. Bye.